Good evening, Bala Murugan. I'm waiting for a few more minutes. Let others join. Then I will start the session. Okay, Bala Murugan.
Good evening, sir.
Good evening, ma'am. Ashish, please confirm whether this screen is visible to you.
Yes, it's visible.
Okay. Okay. Once again, welcome you all in this session 7. So in today's discussion, we will going to look the following topics. Firstly, we will go through Streamflow measurement. Then we will also look into how we can represent the Streamflow data that could be useful for our analysis. Then we will also discuss some numerical examples related to discharge measurement. But before proceeding to these topics, I will add few questions that were left in the previous session. So those questions were related to infiltration and effective rainfall. Okay, so firstly we will go through those questions, like one or two question only, those were remaining, and then we will proceed for today's topics. So I want everyone to kindly solve the questions parallelly. So here the question for the today's session is start from. So it is saying that a 6-hour storm with direct runoff of 7 centimeter and an average intensity of 3 centimeter per hour have the same abstraction as that of 7-hour storm with runoff 8.8 centimeter, and then it is asking that we have to estimate the intensity of 8-hour storm in centimeter per hour. So here we can see that there is two type of scenarios existing, where one we can say like case 1 and we can also say like case 2. So in case 1 it is saying that what is the duration of a storm. So duration
6
of a
hours.
storm here is 6 hour. Then in the second case duration is 7 hour. Then direct runoff is also given, so we can represent it at R. So it is given 7 centimeter. Average intensity is also given, so I am writing it as I average equals 3 centimeter per hour. Then in the second case, what is the data that is given? So here it is asking about intensity. So intensity is not known here in this case, but at the same time it is saying that direct runoff is given, R is given here 8.8. so how we can proceed for solving the I average? Now keep in mind that both these scenarios, they are existing in the same catchment. Okay, they are existing in the same catchment. This is the condition. Now how we can proceed? Any approach from you?
Physics of Thomas.
So see, I average it is asking, so definitely it will be having a unit of centimeter per hour. Okay. Now this rainfall intensity we want to compute in centimeter per hour. So we already have duration, that is 7 hour. Now we need only centimeter, that is depth of the rainfall, right? So how we can
Yes.
get the depth of rainfall? So depth
We
of for
multiply
getting the
7 into 8.8. Okay, this is 8.8 centimeter.
right, this is a
We need
runoff.
centimeter.
Yes.
Okay, okay.
So definitely, if we want to compute rainfall depth, right? So rainfall depth I am writing as P. So if we want to compute rainfall depth, then what will be the P? P will be simply
Distance, time
R
by time
plus
divided by time.
infiltration, right?
Mm-hmm.
If there may be a losses, if it is saying that abstraction is same, right? In the entire catchment abstraction is same. So till now we were solving the problems based on abstraction, where we were finding the phi index, right? So this was the parameter that we were computing in all the cases in order to represent the abstraction magnitude happening in the catchment. Now here we are assuming that this phi is constant. Now runoff we have and phi is constant, we can directly get the value of I, right? That is P. So P will be in somewhat unit of centimeter. But now how we get this value? How we can get this value phi? So for getting this phi value, we have to take help of case 1. Okay. So here you can see that I average is already given. Okay. So here from here we can get that what is the total rainfall happening in this case. So what is the total rainfall happening in this case? How we can compute? P total will
Yeah,
be in unit of
6 into
centimeter, right?
3. Yeah,
Intensity
yeah.
into duration.
Yes, intensity multiplied by duration.
Yeah.
So it will be
18
3
centimeter.
centimeter per hour multiplied by 6 hour, right? So it will be 18 centimeter. You are right. So now we know that P total is 18 centimeter. Also we are knowing that how much direct runoff, how much amount of water is contributed as direct runoff. It is saying that 7 centimeter. So can we determine this in like abstraction depth of
Yeah, it's
losses?
11.
Yes, it will be a losses. So loss in depth, this centimeter. So it will be how much?
Mm.
80, 18 minus 7, that will be 11 centimeter, right?
Mm.
Now, now we want to compute for 1 hour. So we can compute it by dividing it by how much is the total rainfall is given.
6.
Sorry, duration, right? So 6
6.
hour.
We divided by 6.
So whatever the phi value you are getting, you have to take this value here and you have to compute the I value. Okay, so firstly you have to compute this P. Once you get the P value, you have to divide it by 7. Then you can get the intensity value. So look at here. So in this case, so case 1, we were having direct run of 7 centimeter, average intensity of 3 centimeter per hour, rainfall depth we got. You are right, you all gave the reply that 18 centimeter will be the total rainfall depth. Then abstraction, how much abstraction, that is losses. So 11 centimeter were the losses. Then phi index we have computed. So how we have computed? So 11 by 6, that is coming a 1.83 centimeter per hour. Now how we are utilizing this in the next case? So we are taking this phi as it mentioned in the question itself, that abstraction is same. So definitely what is phi? Phi index will be same for both the cases. So now
Mhm.
you got, are you getting this answer? P equals, sorry, this will be not P, this will be I. Okay. So I you will be getting as 3.09. Is it? You
1.83.
use this formula only, nothing else we know we need. So our whatever the phi value you are getting, that is 11 only, right? Sorry, this 11 centimeter by 6 r, right? Now you should multiply this by 7, then you can get the phi value, actual phi value here. Not phi, it will be a losses, right? It will be losses
Losses, yes.
because units should be same na, because
Yeah,
r is in
losses is
centimeter,
equal
then
to
definitely losses will be also be in centimeter. So keep the value in centimeter only and tell me the answer.
1.83 into 7 we have to do. 12.81.
Aha, okay. So how much you
Losses is
got?
12.81.
Okay, 12.81, you are saying that it is coming in centimeter. Then runoff we already know how much it was. It was coming like 8.8, right? So 8.8. So now how much it is?
12.81 minus 8.8.
Yes.
Oh no. 12.81 minus 8.8. No, there is some mistake.
Let me also calculate parallelly. If anyone is getting this
7.
answer, let me know first. Okay.
7 into
Okay, Ashish, you are right that we are
1.23.
getting phi of losses of
Yeah,
magnitude
it's 4.01 I'm getting.
4.01 you are getting. Okay. So if I am not wrong, P should be how much? P total should be how much? It should be 12.81 plus 8.8. Then if I'm dividing it by how much it was in hours 7. No, it should come 3.09. It is right because how much total I am getting? It is coming of about 21.61 centimeter P total. Adding of these two values, I am getting 21.61
Okay.
centimeter. Now if we want to
Okay.
compute intensity, we have to simply divide it by 7 hours, right?
7. Yeah,
Yes. So
3.0809. Yes.
3.09 something, or approx somewhat this much of value you will be getting. Is it okay with everyone? Ma'am, are you
Yes,
getting the
yes.
answers?
I'm getting 3 point,
Okay.
not 9.
Uh, Ashish, you can parallelly keep reminding the answers from Balamurugan, okay?
Okay. Okay. Fine.
Okay, I'm now moving to the next question, okay?
Mm-hmm.
Okay, so here the question again is related to phi index. So it is saying that rainfall on 5 successive days on a catchment was 2, 6, 9, 5 and 3 centimeter. So that means 1, 2, 3, 4, 5, 5 days, and then it is saying that rainfall, that means P total it is saying, and it is coming 2, 6, 9, 5, 3, and these all are in the units of centimeter, and at the same time it is saying that phi is also given to us. So how much phi is given for, like phi will be constant, right? For the catchment it will be constant only. So here it is given that 3 centimeter per hour per day, it should be like that. So it is constant for all the cases. Now it is asking about, we have to compute the total direct runoff from the catchment. So total it is asking. Okay, so cumulatively we have to sum up all these units at the last. Okay, for the
Mm.
firstly we will calculate for individually runoff, we will calculate individually runoff in centimeter, and then we will take the sum of
My.
all these readings together to give the final reading, that will be the total direct runoff from the catchment. So how we can proceed? Like if we want to compute the runoff, right, we already have the value P total, and we also know that phi, but phi should not be like whatever the units you are looking at, you are getting the units in terms of centimeter definitely. Okay, now you have to compute the losses, right? Am I right or wrong? Losses you have to compute, and
Yeah.
losses will be having a unit of centimeter only. So how you can get that? So phi will be multiplied by individual day. Okay, so
24.
yes, day is in the sense, I guess there is no need to change in hours. Okay, so for each case there is only one day.
Okay.
So
Okay.
phi should be constant in all the cases. Okay, you can see here also. So time increment you are looking at in this table, you can see time increment you are looking at, and then infiltration rate is given. Okay, so infiltration rate is constant for all the cases. Now rainfall we have, this is not a rainfall, this is a rainfall intensity, right? Rainfall is given. Okay, so it will be, okay, it is computing the
Intensity.
intensity. Okay, yes, so intensity will be like if we are dividing by 1, then definitely it is coming same value, right?
Mm-hmm.
So it will be at intensity if we are seeing into it now. Or what will be the better from your side, tell me. It is saying that effective rainfall hydrograph we have to compute. So hydrograph will be in what units? Hydrograph, what is hydrograph?
Runoff versus time.
No, if we are
Rainfall
saying that
intensity.
runoff
Rainfall
versus
intensity
time, then it
versus
is hydrograph.
rainfall intensity versus time.
Yes ma'am, right. So rainfall intensity, you are absolutely right. So intensity is here and it is varying with the time, so that's why it is saying that centimeter per day. Okay, so for this case if we want to compute, then definitely we have to compute in terms of intensity, or this is another case, it is saying that rainfall minus input, that is representing the loss, right? So if you are comfortable in computing the direct unit in terms of centimeter, you can do this. There is not a problem. Okay. So how much intensity we were having? This rainfall I am just looking directly. So here you can see that 2 centimeter direct rainfall was given. Okay, in first day. Am I right? Now what was the phi value, or you can say losses? Losses will be nothing. It will be a phi multiplied by time. Okay. So here what was the phi value? Phi was given how much? It was given 3 centimeter. It was given 3 centimeter per day. Now I am multiplying it by 1 day, so it will be definitely 3 centimeter only. Now tell me whether any kind of runoff will be generated if we are facing less rainfall as compared to losses. I mean to
No.
say phi is more than the rainfall, right? So phi is more than that of the rainfall. So whatever the rain is going to take place in that area, it will going to it will not be having any kind of runoff, because whatever is coming, it is whatever is going out only. Whatever the inflow is coming, then that equivalent amount is going out of the system also. So nothing is left now. So runoff will be zero only. So that is why what we are seeing here, that effective rainfall, because for generating the runoff we always need effective rainfall. That is the only thing that will contribute to surface runoff. Am I right?
Yes.
Yes. So here in this case 0 is coming. You already got. So that is why this explanation was mentioned for your information, that if the rainfall intensity is less than phi, then infiltration rate is equivalent to rainfall intensity. Okay. Now in the next case, if the rainfall intensity is larger than the phi, then difference between the rainfall and infiltration in an interval of the time represent the runoff volume. Okay. So this was mentioned for your information. Now in the second case, you can compute the similar way. So are you getting this value? Try to see, try to check this. And at the runoff, what we are doing, we are simply multiplying with the time increment. Like 1 day it is given, so we are multiplying for all the column values. So check and tell me whether we are getting up to this. 11 centimeters should be coming.
Yes, we are getting 11.
Yes, sir.
Okay, that's good. Ashish, can you tell me the response from Balamurgan?
Yeah, he says 11 centimeter.
Okay, that's good. Now, so this is till now we were discussing the remaining portion of our last session. So these two questions were left. Now we are switching to our today's topic related to streamflow measurement, and we will be discussing some numericals on these topics only. So if we are saying that we are concerned for computing the stream flow measurement, okay, we want to measure stream flow. Okay, so can you tell me what could be the possible location where we can measure the stream flow? Firstly, before going to this, I also want one question, that what you understand by catchment? Because catchment is most associated when we are talking about the stream flow. So what is meant by catchment? What you understand by this, and how this stream flow word is related to catchment? Can you tell me? If I am drawing a picture like this, I'm just saying that this is a catchment. Okay, this is a catchment. Can you
The
now
catchment is the
define the
area
things?
from where entire water flows in the one direction
Okay.
to a common point.
Any other responses?
No, sir. The rain falling on that region will contribute and flow reach the outlet common point.
Okay, yes.
Same.
Okay, good. So you are right. So whatever the rainfall falling in the region, so all water, whatever the water it is having in the overland, like it will be a overland flow, that is a thin sheet of water will be flowing over the ground surface, and it will be finally, if I'm just saying that this is a catchment, then this particular catchment will be further divided into some small catchments. So I'm just saying that here the rainfall is falling here. So what will happen, remaining portion what you are looking, this is a blank portion, here overland flow will be dominating here. Okay, and entire water which is falling in this region, it will be getting accumulated, it will be directly draining to a major stream that is in occurring in this region only, in this catchment only. Now you got that this whatever the water, whatever the rainfall happened in this region, it has accumulated or it has been moved into the mainstream. Okay, and now it is following the path and meeting here. If I'm just saying that here I'm having a slope, significant slope, okay, and in this case, in this particular catchment, I'm having some moderate or maybe low condition of slope is occurring in this. Okay, you can imagine that there is a hilly kind of area happening in this region, in this case, in this catchment, and here some kind of plain region is existing. Where would you expect more accumulation of water?
From the hilly region, the stream flow will quickly
Yes,
reach and
reach to the
cause a
outlet.
greater discharge.
Exactly, right. So yes, so in the similar fashion, all the sub catchment will be contributing water to it, to the main stream of this entire catchment, this catchment. And here we are getting the final discharge. Why I'm drawing this? Because I'm targeting to figure out that if I'm just saying that this is a Yamuna river, okay, and I want to measure, I want to get an idea that if I am constructing any kind of barrage or maybe a weir or barrage or maybe a dam kind of a structure, how much inflow, how much water is basically coming and coming as an inflow into this dam. Now if I am just saying that here I am getting 13 million cubic of water, I am getting million cubic of water. So this is the discharge I get. And how I got it? I just got after plotting the discharge versus time graph, right? Discharge versus time. So we got this, and this this 13 million cubic is just a volume only, right? This is representing a volume, and in our previous session also we have tried to compute that area of discharge versus time. It is always giving a unit of volume only. So from this aspect we got the idea of volume, that how much water is this coming. So if we want to construct a dam, in order to distribute this surplus amount of water which is draining in this stream, that is Yamuna only, so we should have some installation of gauge, we should have some stream gauge measurement installed in this region, so as to get the idea that how much amount we are getting. So we can have idea that yes, 13 million cubic of water I am getting in the in the monsoon season. Wait a minute. Okay. So in monsoon season I am getting this much of amount of water, but in case of pre-monsoon, okay, pre-monsoon I am only left with you can say 8 million cubic of water is left in this entire catchment to fulfill the needs. So in order to provide or distribute the water, we are installing the stream gauge stations, and then we are designing any kind of project like dam, culvert, any kind of structure we can go. So here the thing was where we can have the possible location. So possible location will be at where we can get maximum amount of water. So we can plan any kind of structure or maybe water distribution network based on this. So here the question is much more related to this only, that is hydrograph. So technique for separating the base flow and the direct runoff are. So do you have an idea of base flow? So base flow we already discussed that this is a part of groundwater flow only, right?
Yes.
Groundwater flow, and it is counted as a delayed flow also. Delayed flow.
Mhm.
So now that is just because it is a delayed flow, we used to deduct while we are plotting the hydrograph, total runoff hydrograph you can say, we used to deduct this with base flow in order to get the surface runoff hydrograph. So here it is saying that technique by which we can separate the base flow with direct runoff. Okay. So you might have studied these methods, that is one is mentioned here, straight line method, then another one is variable slope method, third one is fixed base method, then the last one is normal depletion curve method. Normal depletion curve method you may have studied that there is one equation that if you want to quantify, that is Qt in terms of Q naught, that is maximum discharge, and e to the power of minus kt. This is some kind of decaying equation you may have studied. So this is a normal depletion curve for base flow. So this is representing this, and then remaining three techniques you already have studied. So tell me that which are the techniques?
The Balamurugan says all are correct.
Ah, that's good. Okay, good. So yes. So if we want to quantify or compute surface flow hydrograph, what we need to do, we have to subtract the base flow, that is a slow response flow, from the total storm hydrograph. Okay, and these are the some terminologies that we already have discussed, that is direct runoff, then interflow. So keep in mind that this interflow is always considered as a quick response flow, that it is getting infiltrated and directly it is coming into the channel. Okay, so that is why interflow is considered as a quick flow. But in case of base flow, it has been found that it is taking a lot of time to travel finally into its final destination. Now what I just mentioned about normal depletion curve method. Okay, so normal depletion curve method was given by Horton in order to deduct the base flow from the total storm hydrograph. So this was the equation that I was discussing. Okay, and then in further case three major techniques were mentioned, that is a straight line method, fixed base length method, variable slope method. They all are based on projecting the drawing a tangential line at B, or maybe where the hydrograph is starting, that is one point, and then where you are observing the change, at one instance while you will start plotting the hydrograph, you will be observing at the last in the recession part sorry, in the that is one of them is rising trend, then another one is recession limb is there, right? Recession limb is there or not? In hydrograph you may have studied, you may have
Yes.
studied the components. Okay, so there is one
Yes.
is counted as rising limb, then another one is
Yes.
recession limb. So when the recession limb is start, that means now the no rainfall is occurring now. Okay, so storm characteristics are not dominating in this, only basin characteristics will be defining this region. Then but once at one time, at any time, you can have some change in this graph. Okay, and that change will be indicating the point where base flow will be adding to it. Okay, so for this case you need to follow these standards. Any kind of any method you can prefer. There is some method which use that is number of days, okay, from the peak discharge we are getting. So you have studied these methods, right? Should I move ahead?
Yes.
Okay.
Okay, please.
So the next question here is the rainfall which is neither retained on the land surface nor infiltrated into the soil is.
This is excess rainfall.
Okay, that's good. Not retained on the land surface. So definitely it is talking about the whatever the portion of rainfall generating as a direct runoff. It is asking
Runoff.
like that, right? So always you know that excess rainfall. Okay, and one more synonym word you also know, that effective rainfall is also used to represent the same case, right? Am I right?
Okay.
Effective rainfall. Effective rainfall is nothing. It is a total rainfall minus what? Losses. Am I right?
Okay.
Should I move ahead now? So this is for your information only. Excess rainfall or effective rainfall is the rainfall which is neither retained on the land surface or not infiltrated into soil. Then you also already know that if we are plotting a graph of excess rainfall versus time, we are getting a excess rainfall hydrograph, that is ERH. Most of the question we already discussed that if we are subtracting the total rainfall hydrograph from losses, we will be getting excess rainfall hydrograph. Then that is important for studying the rainfall runoff relationship. And then you can also see that difference between the observed total rainfall hydrograph and the excess rainfall hydrograph is termed as abstractions. We know that. Then losses are primarily water absorbed by infiltration, and maybe they may be getting intercepted or may be stored in surface depressions. Now just for your information, I have just added one picture which is representing both input as well as output. So input here is what? Input is representing as rainfall. So you are seeing a graph that is like rainfall versus time. Okay, so you are seeing this picture. Then in parallel, output, that is a response, have been plotted in terms of you can say stream flow. Okay, so like if we are getting a higher rainfall value, or you can say excess rainfall we are getting after subtracting the losses, then definitely there at that time we will see a high peak while we are plotting the direct runoff graph. Okay, so this is the peak that we are getting corresponding to higher excess rainfall happening in this time frame. Got it? Now coming to the next question. So it is saying that stage discharge relationship was also known as. Like there is one more word that we used to take as an input data. Okay, like while when we are in the field, I just want to mention one thing, that if we are having any kind of stream channel, okay, and we have installed a gauge, okay, so for getting the discharge data continuously, there is one process that usually all CWC stations do. What they do, they usually firstly establish the stage versus discharge data, okay, that is Q. So firstly they used to establish the relation between stage and Q. So definitely Q will be in terms of some constant versus stage will be in terms of H. So this is the equation they establish for this cross section only, this particular cross section. This relation can vary depending on the cross section. If we are taking a cross section in this case, then definitely we have to again establish this relation Q versus H. So constant is nothing, this constant is just representing the behavior of this cross section, okay, in this stream channel. So now once they establish this stage and Q relation using the past year data, okay, past year data, they can establish this relation, and this relation is can be like valid for maybe 1 or 2 years only, because after that they are assuming that this cross section may get changed. If surplus amount of sediment flow is happening in this cross section, then sedimentation, because of the sedimentation problem, there could be a possibility that carrying capacity of this river may get low, okay, carrying capacity in the sense what, that is I am talking about volume. So volume may get lower if significant amount of sedimentation is happening. So that is why they used to like repeat this relation, like cross check this relation after every coming monsoon season. So once they get the H value, now see, now what they do, once they establish this relation, what they will do, they will only take the H value reading every day, okay, and for this staff are installed at every CWC station. You might have seen any CWC station, then there is graduated staffs are installed. Usually you can find it like beneath the bridge, okay, if there is a river flowing and there is a embankment already plotted there, so you can see these kind of staff, okay, and this is representing the water level, that how much depth of water is there. So just taking out the reading of this, so if I am saying that H is somewhat 3.2 meter, and keep in mind that these all readings will have some RL also, reference level, and these reference level will be corresponding to MSL only, MSL in terms of from the MSL how much it is above or below, like above only it will be mentioned. So it will be like you can find these value in every staff gauge stations, okay. So if you got the value like water depth, you are getting 3.2 meter, just simply put this in this equation and you can directly get the discharge value. So this is the procedure CWC station used to do when they are maintaining the data, like past record data they are maintaining, okay. So now it is asking that stage discharge relationship is known as, like there is one alternative word for the same thing.
Rating curve.
Yes, rating curve, right. So rating curve is the answer, because hydrograph you already know. Mass curve, you know that this is the cumulative rainfall versus time graph. Then routing curve you will be getting in further case, like this is for the dynamic case when the like flood kind of situation is occurring, then how we are approaching, then we will be studying in the further sessions what is routing curve is there. Then yes, stage discharge is a rating curve only. So here just what I just mentioned, that two-step employment in the stream flow measurement, that this is the two-step process. You can see what I just mentioned. So discharge of the stream is related to the stage using series of measurement. Okay, a stage discharge relationship is developed, that is known as a rating curve. Now in the second step what they are doing, water level or stage is routinely observed. So now they are taking the H value only at every day, and corresponding they are measuring the discharge data from rating curve. Got the point? Okay. Now I guess you all may be knowing the things. One more important line is mentioned here, that if we are preferring this stage discharge or maybe rating curve, then it is somewhat inexpensive, okay, and it is also less time consuming also. But if we are going directly into the river, like we are carrying the current meter, or maybe we are okay, or maybe we are taking a boat method, it is also there, okay, and at the same time area velocity method is there, slope and other methods are also there. So for that case it is saying that direct measurement can have time consuming also. Okay, the next question here is a very thin sheet flow which occurs at the upper end of a slope before the flow concentrate into a recognizable channel. So
Overland flow.
Yes, so it is just saying that this part, this is a thin slit where this is a empty region, just I am mentioning, highlighting here. So here it is asking about this. So yes, overland flow is the answer. Once this water will get accumulated, then there start the surface flow, because now entire water have been guided in a particular stream. So here it is mentioned that the flow of water over the watershed surface begin when the water become ponded on the surface. Ponded in the sense what? Infiltration capacity is maximum now. Okay, what like maximum amount of water which can be hold, which a soil layer can hold, it is now got the maximum value. So that is after that point only ponding process will start. Water is not infiltrated anymore, it is just getting ponded over the surface. So this is the case. So on the surface at sufficient depth to overcome the surface retention forces and begin to flow. Now begin to flow, that how overland flow can be possible and channel flow can also be possible. Overland flow is what, that you already explained better, that it is a thin sheet flow that is occurring. Now if we are saying that channel flow, then that is a narrower stream of water flowing in a confined path. So whatever the overland flow of water it is getting accumulated in the channel flow, that is the thing. Now the next question here is, discharge is higher on which side of flood hydrograph?
Rising limb.
Okay, rising limb. Good, you are right. So if we are saying that flood hydrograph, so definitely there will be a shape like this. There will be a certain kind of d duration of graph may be there. So we are getting the discharge value here and we are getting the time. So yes, if I am saying that A, then I am saying this B, and then I am saying this C, and maybe D also. So AB part is rising part. Okay, so this is representing the accumulation, like it is representing the combined effect of basin characteristics as well as the storm characteristics. You should you should remember these things in these two major terms. One is storm characteristic. So AB, that is rising limb, this will always get influenced by storm characteristics. Okay. So storm characteristics means what? That is talking about the intensity. Okay, intensity is high, then what would be the effect? Then how much duration is happening, that is also a storm characteristics. Then another case also come, that is a basin characteristics. So basin characteristics also plays a significant role in controlling the discharge. Basin characteristics means what? That is talking about the size, that is talking about the shape. Okay, that is talking about the LULC pattern, land use land cover pattern. So these all points have to be taken in mind while we are predicting the discharge at the outlet. So for this case, yes, discharge will be higher when we are counting the rising limb. Okay. Then, okay, so components of a storm hydrograph, you all are aware of this. Okay. Now
Yes.
there is one important point that I want to highlight, is that point of inflection. So this is a starting point of recession limb. So recession limb is what? That is P.
P.
Okay. P or D? P
P.
is the peak.
P is a-
Yes, you are right. So starting point of the recession limb, it is saying that. So P definitely just after P only it will be. And then flow is contributed from different storages of the catchment. Like wherever the water have been get stored, now that water is now just coming out. This is the thing representing by this. Okay, one more thing you can see that whatever the things we have just discussed, that basin characteristics control the shape of falling limb. Falling limb means what? That is a recession limb only. Okay. Okay. The same question here, it has been mentioned also. So it is saying that shape of the falling limb is dependent on.
It's basin and storm characteristic.
It is no. I just mentioned that
Oh, the shape of the falling limb. Okay.
falling limb in the sense you will not getting any kind of storm characteristics now, because rainfall is not happening now. Rain has already stopped. So in this case, only basin characteristics will play a role, because wherever the depressions may be there, wherever the water have been it have been stored in the depression, now that water will start accumulating and it is now coming to this point. And that is why you always have noticed that always peak time is always less. Like time to reach the peak is always less compared to the falling limb. Falling limb will go like this. It will take time. Why? Because these water which have been stored in the depression, it will take time to reach the outlet. So that is why this part will take more time. Okay. So here you can see catchment characteristics plays a role here. So in this case, what are the catchment characteristics that have influence in this case? So shape is there, and size is there, slope will also play a role, then drainage density is there, topography, then geology. Drainage density is basically represented that how many streams are there in a unit area, you can say. If I am just saying that this is a catchment, now how many streams? If I am saying that streams are too much, like these are the all are streams, and I am saying that this is only a 1 kilometer square of area, and if stream drainage density is more, then definitely there is more possibility of water to get to the final outlet point. Okay. Now geology will also have a role. If there is I'm saying that metamorphic type of rock, if it is there, then definitely there could be a possibility of sand. Okay, sandy, if there is sandstone, if I'm saying, then possibility is there that base flow will not be getting that much delayed, and it can directly it can contribute to the stream flow in minimum time. That could be the possibility. So from this picture you can have one idea that if we are having elongated kind of basin or catchment, then we are getting the duration and peak. Duration is always high and peak is always less. If we are getting nearly circular kind of shape, then flow is always like peak is always high at minimum time. Okay, duration is very minimum. So this is the thing mentioned here. Next question here is the shape of rising limb is dependent on.
So it's basin and storm characteristic.
Yes, right. So whenever the rising limb is there, so whatever the input rainfall is coming, so that is contributing here, that is causing it, that is the only thing defining its shape, that how it should rise. So right, basin and storm characteristic both. Okay, so here one additional thing was there, storm characteristic. So here it is mentioned that total rainfall depth, it is one of the parameter, then intensity of the rainfall is one of the parameter, then duration of the rainfall. Intensity is high or duration is low, or maybe duration is high, then depending on these situation, there is possibility that these peak as well as the duration of this hydrograph may be affected. Then again the question here is, you have to answer here. Nearly semicircular shaped catchment have the following criteria. Now you have to figure it out, what could be the possible situation may exist. Just I mentioned you that picture now, based on this only it has been asked the question. If we are having a semicircular shape of catchment, what could be the possibility? Like it is asking in terms of peak as well as the duration. So what could be the situation now?
Yes, high peak then elongated catchment of the same area.
High peak, which option?
Second.
Okay, second option you are saying that higher peak than that of the elongated catchment of the same area, right? So you are saying that
One also is correct. Shorter runoff duration than that of an elongated watershed of same area. One also will hold good, I think.
Yeah, right. So
Yes.
you both are correct. So first and second.
Bala Morgan also says 1 and 2 are correct.
Ah, that's good. Good. So first and second both options are correct here. So if we are getting a nearly semicircular kind of catchment, then we can see that duration of the rainfall, duration of this flow hydrograph will be less, right, as compared to elongated one. So elongated, for the elongated case you are saying that duration is much more higher, and also peak is less. So peak here in the case of nearly circular, we are observing the high peak. Then there are some more conditions are mentioned for your information, that for what case we can have early peak, then we can have a delayed peak, then multiple peaks or can also be there, then this kind of flow graph you may be getting. If we are having a delayed peak, that means you are this region, this particular region is causing it to have a delayed peak, because if you count this part, then this is entirely a circular one. it can generate a flow in quick time, but as the water needs time to finally reach its outlet, so that is why its peak is getting delayed. Then early peak can also be there if it is getting more and more circular. So now entire water is getting and reaching as quick as possible. Okay, now we are heading towards stream flow measurement. So the question here is, which of the following is not used for the stage measurement? So I just mentioned where it is useful. I just want to know stage measurement is useful. How we are using this? In which method we are using this? Just I mentioned here, that is rating curve, right? Q versus Q in terms of, you can say, H, right? Q in terms of H. This is a rating curve. That is a relation between discharge and stage and discharge. So for this case, stage measurement is important. And now it is asking that what are the methods through which we cannot measure the stage?
Balamurgan says it's current meter.
Yeah, yes, current meter. Okay, so current meter is what? For what purpose we are using the current meter? What it is
Measures
measuring?
velocity of flow.
Yes, ma'am, you are right. So velocity it is measuring meter per second. So there is a assembly called cup shape assembly is there, which is getting revolved, and after counting the revolution of that cup assembly, we are getting the velocity. For velocity, for this case, we need we have some relation for establishing the velocity. So V is A plus B into N. N is representing the revolution of that cup, and based on that we are computing the velocity. Yes, and remaining all these methods we can measure the stage. So here it is mentioned that non-recording type is also there, and then recording stream stage measurement is also here. If we are talking about non-recording, then staff is here, then wire gauge can also be used, then electric tape gauge can also be used. For detailed description, it is mentioned that staff gauge can also be divided in two cases: vertical staff gauge, and then another one is sectional staff gauge. So this was the thing that I was just mentioning, that CWC people used to follow this kind of assembly. They used to install the staffs and try to gather the readings from here and directly computing the Q using the rating curve. Then there is wire gauge also there, using the bridge kind of assembly. Okay, now we are moving to another question. Most suitable method to measure the stream flow in stony mountain streams is? So for measuring the stony mountain stream is why? Because it is having more steeper, they are more steeper. Also most of the time they are also inaccessible. We cannot install the rain gauge station directly in those locations. So for that case, we use a kind of we can say direct method, that is dye injection method, or maybe you may be knowing this in this word, dilution method. Okay, so this method is useful. Moving boat method, it can be useful when the river is having more width. Like if you are targeting entire Ganga river, okay, so there may be a stretch where you will be getting the width of about maybe more than 50 meters also, okay, greater than 50 meter. So for that case, boat method will be a good option. Now this dilution method, do you have idea that how we can measure the discharge using dye injection method? So for this case, firstly we have to select the two sections, that is one section, this one, then another one is section 2. Now we are adding like a known concentration of salt solution. You can say, I am just saying that I am adding 20 milligram per liter of salt solution in this region, and now I am trying to get the value here at at section 2. I am having like direct measurement in situ instruments are also there, which can directly measure the level of salt at this location. So based on that, I can get the idea that yes, I am getting somewhat value, maybe you can say 16 milligram per liter. Now after getting this C1 and C2, also the rate of application, that is rate of application may be QT. So there is one empirical relation which can help in computing the discharge Q. We can get it easily from that equation. We will discuss, we have one problem at the last slide, so we will look into that also. So direct measurement of a stream flow can be possible by using area velocity method, moving boat method, dilution technique and ultrasonic method. Dilution method is mainly suitable for stony mountain streams. Also moving boat method is suitable for wide rivers. We also have indirect methods, like we can measure the discharge from flow measurement structures, like that is where maybe there may be a flumes or maybe a gated structure, that is a dam or maybe a spillway kind of structure may be there, and we will be getting the value in terms of y, that is q in function of y. One more indirect method is there, that is slope area method. This is based on the law of conservation of energy, and we need to incorporate uniform flow equation. Now we are here in the numerical question. So you can see a question problem here. There is a salt solution of concentration 15 milligram per cc. Cc in the sense means what? Cubic centimeter. Is introduced into a stream with no trace of salt initially. Why is it mentioning that no trace of salt initially? Because it is saying that if I am having a stream, whatever the water it is flowing, already flowing here, it could have a possibility that dissolved salts may be there, right? So in order to test this this method, firstly we have to know that what is the initial dissolved salt concentration. Otherwise we get some disturbed value, because if I am just saying that I am just giving 20 milligram per liter of salt solution here, I am giving, okay, I am applying here, and I don't have idea of dissolved salt concentration, then how could I say that whatever the concentration I am getting at the downstream section, it is accurate? Definitely it won't be, because if we don't have idea of dissolved salt concentration, we cannot get the correct value, because we have to subtract this dissolved salt concentration from the initial, whatever the value we are giving, then only we can compute the final one. So For that case, there is an assumption in this question that initially no salt is present. Now, what is the rate of application of that salt solution? This salt solution was added in the river, right? And what is its rate? Rate is what? 1.45 liter per minute. So 1.45 liter of salt solution we are adding in 60 seconds. So this is the thing mentioned in the question itself. Now at the downstream section, that is section 2, sample have been collected now at the downstream section. Sufficiently far away indicated an equilibrium salt concentration. Now how much concentration they are getting? 0.02 ppm. ppm is nothing, it is a unit of milligram per liter. It is equivalent to milligram per liter only. Now the question is asking that we have to determine the discharge in the stream from this data. We want to compute Q. Any idea from your side we can approach for this question? You may have already studied this topic, I guess, right? Ashish, any idea?
No idea.
No idea. Okay. So I'm just saying that for solving this particular aspect, this question, we need to use mass balance approach. Mass balance approach. So whatever the inflow concentration we are giving minus outflow concentration we are getting, and we are saying that the remaining part, whatever this
It's change in
yes, change in storage,
concentration. Okay.
right?
Storage.
So based on this this principle, continuity principle, we can determine the discharge in the stream. Now firstly we will see the expression for this question, what expression we are going to use in this case. So here dilution method will be used. So dilution method of flow measurement, also known as a chemical method, which depends on continuity principle applied to a tracer which is allowed to mix completely with the flow. So here you can see, you can observe in this graph itself that initially C0 is what? This is a dissolved concentration already present in the water before starting the test. So firstly we measured the dissolved concentration, that is C0, and you can also say in other words that is a background concentration. And then we have applied certain amount of salt solution at section 1. You can see concentration level here, C1, and after some time, or maybe after some distance away from section 1, we are getting the curve, constant curve like this, that is C2. So at steady state, if we use the continuity equation for tracer method, we come up with this QT. QT is basically, you can say, rate of application, rate at which we are applying the salt solution. So QT in our previous, in this question, it is mentioned at 1.45. C1 we know that initial concentration. Q is not known.
0.
C0. C0 here is 0.
No.
Also
0.
Q plus QT, and we are multiplying it with C2, and after solving this we are getting this equation, and this equation is what? This equation will only valid when we are applying a constant rate injection in the river, because in this question itself it has been mentioned that we are applying the salt solution at a constant rate. There could be a possibility that we can apply a salt solution suddenly, then this entire this graph will get changed. This graph will be coming like this. In this case there will be a background concentration initially, then we have suddenly added the concentration, so salt concentration whatever the we are measuring in the river, it is getting more, and then it will finally come to its original level. So this is the case where we are getting a sudden rate of injection, but in this question it is saying that we have to use the constant rate injection method. So all these, if we are knowing the C1, C2, C0 as well as QT, we can directly compute the Q now. So can you compute now? Can you try to compute this value Q? So what we have? We have QT equals 1.42 something or 45 liter per minute, right? And then what are the other values? C0 we got, C0 is 0. How much is C1? C1 it was, how much it was? 15 milligram per cc. 15 milligram per cc. Cc is nothing, it is a liter only. 1 liter equal to 1 cc. Am I right, Ashish?
Yes, correct.
Okay. So C1 is known to us, and also C2 we know. How much it was? It is 0.002. So 0.002 milligram per liter. Any value is missing here now? For time being, you can convert this QT in I will say or directly you can convert, like you can compute in liter per minute first. Firstly compute the entire Q value in liter per minute, then you can convert in meter cube per second. Later you can convert it. So firstly convert this and tell me the value. I am also computing parallelly.
One 10873.
What
No,
you are
no,
getting?
that's
1083. What is this? Q.
minus 1002 divided by 1002 C2 into 1.45. I'm getting 10873.55.
What
Q.
is this? Q.
Q.
How much?
Q.
How much?
10873.
10873 liter per minute.
0.55. Yeah, liter per meter cube. Liter per minute.
Okay. Try to compute in meter cube per second now.
So, okay. 10873 into 55 liter per minute. 10873.
For liter to meter cube, you have to divide it by 1000, right?
And multiply by 60.
Yes. You have to divide it by 60, na?
So 652.
652 you are getting 652 meter cube per second.
Yes.
Okay, wait for others to solve. I want others also to answer this, and let me solve till
652.41.
okay. So it is in meter cube per second.
Yes, meter cube per second.
What is the value? Q is 654.
52.
Okay,
52.41.
41 meter cube per second. Okay, let's wait for Bala Murugan reply also. I can check also. Wait a minute. Okay, Bala Murugan. Okay, Bala Murugan, you are getting 181.25 meter cube per second. Okay, got it. Okay, you have replied almost every answer. Good. Good. Yes. Okay. Okay, I'm just moving ahead. Then you can match with the slide, like whatever the solution mentioned in the slide, you can compare with that. Okay. Okay, so just for your idea only, the again same whatever the like calculation which was mentioned using the continuity equation. So here you can see this is the rate Q meter cube per second. This is the rate. C1 is the initial concentration. C0 is a background concentration. Then C2 is the final concentration we are measuring at the downstream section. And now after that we have applied the continuity equation, and continuity equation can be written in this final expression. Now it is also mentioned that if in case initial concentration, that means initial in the sense what, that is a background concentration, and if background concentration is missing, then we can directly use this equation, that is Q C1 upon C2 minus 1. Now see, okay, so the answer is 181.25 meter cube per second. So I guess Bala Murugan solved correctly. So here try to see how we are getting this. So C1 was how much? It was 15 milligram per cc, that means 50 milligram per liter I can write. Now 0.002, how much it is coming? I'm solving now.
Okay, we are solving again. C1 is 1.45 by C2. Into what? Into Q is C1. Okay. It's correct. We are getting the same.
How much?
Divided by 1000.
Are you dividing it by 60 or not? Because it should be meter cube per second. So it will be divided by 60 only. See,
10873.55 divided by
10873, right? You are getting this.
yeah divided by 60.
How much? You are dividing it by 60. Yes, because it was in liter per minute, na?
Then how it comes meter cube per second?
No, no, no. I'm just saying that it was initially liter per minute, right? So liter,
Yes,
if
yes.
we are converting 1 liter to meter cube, then what we have to do?
Then we need to divide it by 1000.
1000, right? So 1000 is here. Then
Yes.
for minute
Then
we
we
have
need to
to,
multiply it by 60 to get it into the meter cube per second.
yes,
No, 60 will come on top
60 will come on top.
because we are now we have to multiply it.
Wait a minute, wait a minute. Ma'am, what is your answer? Are you getting anything? Like,
Yeah, liters per minute is a smaller value. Liters per second should be a great. I'm sorry. Yes, should be liters per minute. You convert it into meter cube. Then to get it for seconds, I think because minute is in the denominator, you have to multiply it by 60. No.
yes. Ashish, look. If we are saying that there is 1 liter, na, right? So if you
Yeah,
want to convert this, we have to divide it by 1000.
1000.
Then
1000.
it will be converting as meter cube, right? Now
Super.
we
Yes.
want to convert this minute into second, right? So 1 minute is what? 1 minute will be 60 second, right? So we can directly put
60.
it as 60 second, na? What is the problem?
Okay. Okay.
What is the
I
problem? I
think
am just
the
asking.
Mm-hmm.
Any problem? Like minute should be converted directly now. I'm just putting 1 minute.
yeah,
I'm
yeah, yeah,
considering as 1 minute and
yeah, yeah. We confused. I think. Right. You're right.
hmm.
10873 divided by 1000 divided by 60. Then it comes 0.181.
Okay, 0.181. Okay. Balamurgan, I just want to know that. Okay, check. Firstly, check the this values first. Okay. Wait a minute.
This is 15
Why is it
into
coming? It should come 181 only. We are converting the
what
units correctly or not?
Paramorgan says 15 into 10 to the power as a parts per 15. Okay.
Okay,
I think
he's
we need
saying
to convert this cubic centimeter to meter cube.
yes. He is right. Okay,
Yeah,
check
yeah.
the number. 15 milligram is 15 milligram per liter unit is not correct. Okay, okay, okay,
We need
okay.
to convert cubic centimeter to I think this one.
Okay, Balamurgan, I'm just checking. Wait a minute. Milligram question. It was mentioned like that only now. Milligram per cc. What is the problem? 15 milligram per liter. 15 milligram per cc it is mentioned.
So that centimeter cube has to come to metric meter. No. I think that conversion also has to be.
Nah, yes, 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 right. So 1 cc it will be multiplied by, yes, right, it will be multiplied by 1000 only, right? Ashish,
Mm-hmm.
it will be multiplied by, yes, 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 good. Now you can get this value. Good, Balamurugan. Nice. So these kind of confusions occur usually while solving the problems. Though we have availability of calculator and all, firstly we have to look the question first. That is the thing. Got it? Ashish, getting the answer or not?
One minute, I'm doing it. C1 is equal to 3.
Okay, now I am getting. Ma'am, are you getting the answer? Are you able to calculate now? What we did,
I'm just calculating again.
yes, actually
because
what we did, we have just milligram per cc, and if we will convert the cc to liter, it will getting multiplied by 1000, right? And then we will getting direct value of milligram per liter. So 15,000 milligram per liter, it will be the value of this conversion. And then go ahead and solve this expression. ppm is nothing, it is only.
Yeah, then we get 181.25.
Ah, that's good. Yes. So keep the conversion in your mind while solving this problem, such problems, okay? This is like one of the best measurement tool that exist, because like in this method have been performed from myself also. Like I was in the field and I performed 3 type of methods. Like first one was current meter. So current meter was in we were getting the velocity value, and at the same time we are getting the depth of water, because when we are carrying the current meter, so current meter assembly is always come up with a one rod.
yes, I also got 181.25.
Ah, that's good, ma'am. Okay, good. So what I was just mentioning that if we are having a current meter kind of assembly, then we have also provided with one rod which can measure the water level. Okay. And after getting the area and as well as the velocity, we can have like computed value of Q. Okay, so this is the current meter through which we can work it out. Now the second method which I preferred was float method, that we did in our childhood also, like just selecting the stretch of river and just throwing any kind of like light weighted material, maybe a wood you can throw, or maybe a boat like this paper boat you can make and you can use in this river. What you have to do, just firstly predefine this length, so you will be having a distance known, and then try to measure the time, that how much time will this wood take in order to reach from one point to another point. So So now this divide this distance with the time, you will be having a rough idea of river flow. So this is the float method. Then third one was what? That this dilution method, dye injection method. Okay. So dye injection method, for this one need to be more cautious while preparing the salt solution. That is important, because if there is an error, definitely you are not getting the accurate result. Okay, now I am moving ahead to the next question. Okay, so the question here is related to urbanization. So it is asking that if the urbanization is increasing in any area, the following condition may exist. You may be knowing this word urbanization. Urbanization means development of an area, like more peoples are migrating from rural to urban. So definitely there will be more construction you will be observing in this area. Okay, and because of more construction you will be observing
Runoff.
yes, more
Runoff will
right,
increase.
yes. So what could be the possible like condition which may exist here? So one is saying that infiltration may increase, then another one is high flow peak may occur at a shorter duration, then increase runoff volume, then velocity of the flow may be high. So now
Second, third.
okay, so you are saying, Ashish is saying that second and third is there. So high flow peak you are saying, right, at a shorter duration possible, yes, because what is happening is just right. So at minimum time peak will be generated. Now you are saying that third one is also right. So increase runoff volume, yes, of course, runoff volume will be more. And then runoff volume in the sense what? If we are taking out an area of this hydrograph, then you will be having an increased runoff volume. Then what is next? Velocity of the flow may be high.
It's also correct.
Yes, of course, it may be. It definitely, if there is, you are saying that like pavement kind of a structure is there, rainfall is falling, then definitely what there is no obstruction in the path of flow. So definitely flow will be this velocity will be high, right? So this could also be a case. But what about one? Will it satisfy this condition?
No.
No, 2,
Yes.
3, 4 only.
2,
One
3,
will
4
not
is correct,
be
right?
correct.
So 2, 3, 4 is correct in this case. So we will look into the explanation also. So look at this graph. Before urbanization and after urbanization, you can see the difference in the hydrograph. If we are saying that after urbanization, so there is a high peak as well as low duration, shorter duration you can say. And in the other case, before urbanization, duration was more and peak was less. So what is the major changes that you are observing when we have an urban watershed? So first one is volume of water available for runoff increase. Why it is increasing? Because of the reduction in amount of infiltration.
Yes.
And one more important word you have to note it down, imperviousness. Because of the more construction,
Yes. The ground become impervious, so there will be
yes,
more runoff volume.
exactly right. And what kind of structure you can see? That is parking lot, streets, roof, you can observe anywhere. Then the second option you can also prefer. Velocity of the flow and magnitude of the flood peak are increased because of the artificial channels are there. Gutters can also be found in urban area. Storm drainage also you can see. So these kind of artificial structure, because of this you can observe high flood peak as well as high velocity. So in summary it has been mentioned that effect of urbanization on the flood hydrograph include increased total runoff volume as well as the peak flow rates, both the cases. Got it?
Got it.
Okay, so this is for today's session only. If you have any doubt, we can discuss. I'm just now. Okay. 4 also correct. Okay, Bala Murugan, you replied yes. Good. Good to see that you all are like doing efforts in parallel with me. Okay, okay, good. So this is for the today's session. Like
Thank you.
there are some more numerical problems related to current meter. Okay, so I will try to compile them in the next session so that we would able to solve the field problems also. Like whatever the data we are measuring in the field, like can we compile, like we should have some idea that yes, how CWC is measuring, like for the case of rainfall, IMD, how they are measuring the data, how they are computing the data, then CWC, how they are measuring. So we should have some idea related to this. Okay, we will discuss in the next session also.
Sorry, sir. Around 7 o'clock, I had some connectivity issue, so I got disconnected for about 10 minutes because of net issues.
Oh, okay, okay, okay. We want
So I missed little.
Okay. So, ma'am, like if anything is missing, you can tell me. I can like I can try to help you.
I think I missed questions 4, 5, and I just joined in the mid of discussion of 6. I can even see the recorded session.
Ah, yes, yes, ma'am.
If I need not trouble you.
Oh, okay,
Thank you.
okay, no issue, ma'am.
Thank you very much. Thank you.
Yeah.
Thank you, sir.
Okay. Okay, then we will meet in the next session. Till then, bye. Take care.
Okay, thank you. Bye.
Okay.
Thank you very much. Thank you, sir.
Hmm.